So now we know how to compare two different proportions. That is, if we have two different independent samples and we want to compute things about the difference of the two probabilities, like confidence intervals and hypothesis tests, then we know how to do that. What about for means? What if we have two different samples of means and we want to compare those means, or say things about the difference of those means? Well, we can do it again, and it's pretty similar to the previous case, but it's a little bit trickier, as we'll see. So to start off, let's again remember what we know about one sample. In this case, one sample for a mean. Well, we know that if we have a sample with some size and some x bar and some s squared, then we had this distribution equation that said if you take x bar minus mu and divide by the square root of s squared over n, then that will have approximately a t distribution. And the number of degrees of freedom will be n minus 1. And this is good because it allows us to compute confidence intervals and allows us to do hypothesis tests and so on. What about if we have two independent means? So they're not matched, they're not paired up in any way. We just have two different samples, and we'd like to know something about the difference of the two true means. Well, again, the samples would have different sizes, n1 and n2, and they'd have different values of the sample mean, x bar 1 and x bar 2, and they have different sample variances, s1 squared and s2 squared. And we'd like to be able to say something again about the distribution so that we can compute confidence intervals and do hypothesis tests. Well, here's a fact, and it's what you might hope is true, that if you take the difference of the x bars and subtract the difference of the true means, mu1 minus mu2, and divide by the square root of some sort of a variance, then maybe it still has a t distribution. And it's a fact that approximately it does. This isn't quite true even in the limit of the central limit theorem and normal data, but it's approximately true. And the variance that we divide by on the bottom, well, it's the square root of a variance, and that's kind of what you might expect. It's the sum of the two different variances, the s1 squared over n1 plus s2 squared over n2. So that's good. The most surprising thing here is, what is the number of degrees of freedom, df? Well, turns out to be given by this rather complicated equation here, sometimes called the Welch-Satterthwaite approximation. And anyway, it's some sort of a complicated formula that gives us an approximate number of degrees of freedom to make this quantity approximately have a t distribution. Now, this number of degrees of freedom might not even be an integer, but that's okay. The t distribution can still make sense and can still be computed on a computer, even when the number of degrees of freedom is not an integer. It's something with a decimal point. So we can use this to get confidence intervals and hypothesis tests. So let's start off with confidence intervals. Now remember what we know. We know that we take this difference of the x bars minus the difference of the true means and divide by the square root of these sums of these two different sample variances. Then it has approximately a t distribution with some number of degrees of freedom given by that crazy formula in the previous page. And so then you say, well, can we get a 95% confidence interval for the difference in the true means? Well, sure. It should be the difference of the two sample means plus or minus the critical value t times the square root of this sum of the sample variances. Now, this critical value t corresponds to whatever significance level we've chosen, like alpha could be 0.05, and the number of degrees of freedom from that formula that we had. So t might be a little more than 1.96 in a typical example. So this is easy. Let's see how it works in an example. Let's go back to our friends the skeletons, and let's consider now, suppose we wanted to compare these age differences depending on the gender of the skeleton. So let's recall that we had 400 skeletons in total, and each one of them had some age difference between the estimated minus the actual age at the time of death. Now, for the male skeletons, there were 281 of them, and they had their own mean for the age difference, which worked out to minus 12.9 years, with their own sample variance of 181.5. And the females, well, there were 119 of them, and they had their own sample mean, in this case minus 17.1 years, with their own sample variance, in this case 231.5. So that means the difference in the sample means was equal to 4.2 years. But the question is, what does that say, if anything, about the difference of the true means, that is, the true age difference for male skeletons minus the true age difference for female skeletons? Well, first we have to use that crazy formula from before to get the effective degrees of freedom, df. In this case, it works out to just over 200. And then we have to get the computer to help us compute the corresponding critical value. And it works out to 1.97 in this case, which is just a tiny bit more than the 1.96 it would be for the standard normal distribution. So then a 95% confidence interval, well, it should be the difference in the sample means plus or minus this critical value of 1.97 times this square root of the sum of the sample variances, which works out, when you put in the numbers, to between 1.03 years and 7.37 years. So in other words, we're saying that this age difference quantity is indeed higher on average in the males. It wasn't just a fluke of the samples we got. It's a true fact, and this true difference, the mu1 minus mu2, the true difference between the means, is somewhere in this range. So that's the confidence interval for the skeletons. Let's do a second example. Let's remember that map of the world and how we had different regions. And in particular, we considered life expectancy. In one region was East Asia and the Pacific. Another region was South Asia. And we could say, well, what's the difference in the life expectancies in those two regions? Well, in this case, we can start by remembering the facts and figures. So East Asia and the Pacific had 30 countries. Their mean life expectancy was 73.1 years with their sample variance. And South Asia had just 8 countries. Their sample mean life expectancy was 67.0 years with their own sample variance. So that means the difference in the sample means is equal to 6.1 years. And again, we can say, what does that tell us in the difference in the true means? Now, I should say that in this case, in some sense, there is no true mean because we just have these countries. There's not some overall population. But we can imagine there is. We can imagine, as we discussed before, a typical population of countries from East Asia and the Pacific and a typical population of countries from South Asia. And we're looking to see what the range is, or the confidence interval, on the difference in the means of these imagined theoretical world populations. So in this case, we again use that crazy formula to compute an effective number of degrees of freedom. In this case, it's just a little more than 9 because the sample sizes are so much smaller. And compute the corresponding critical value, which in this case works out to 2.26, so a little bit more than the 1.96 that it would be if we had a really large sample. And then we can plug in the formula and get a 95% confidence interval, again given by the difference in the means, plus or minus this critical value 2.26 times the square root of this sum of the sample variances. And when you stick in the numbers and work it out, we get a range from minus 1.2 years up to 13.4 years. So we're saying at the 95% confidence level, East Asia and the Pacific could have a life expectancy which is lower by as much as 1.2 years, or which is higher by up to 13.4 years. So that tells us about confidence intervals. What about hypothesis testing? In a hypothesis test, we usually want to test whether the true means of the two different samples are equal to each other, that's the null hypothesis, or they're different from each other, that's the alternative hypothesis. Now remember what we know. We know that this statistic, this difference of the sample means minus the difference of the true means divided by the square root of the appropriate sample variance, is approximately a t-distribution with some number of degrees of freedom given by that complicated formula from before. So we can use that to compute p-values. Now, one thing you might wonder, if you remember what we did with proportions, we said that under the null hypothesis, we were assuming the two p's were equal, so we could kind of pool our estimate and get a single pooled estimate for p hat. Well, in this case, you might wonder, under the null hypothesis, can we again pool things together? Well, the answer is no, unless we also assume that the two samples have the same variance. If they have different variances, then even if they do have the same mean under the null hypothesis, we can't pool them. So for now, we won't do any pooling, but at the end of this lecture, we'll consider the possibility of pooling if we assume the variances are equal. So for now, let's go back to that skeletons example, and remember we had the two different samples for the male skeletons and the female skeletons. They each had their sample size, their sample mean, and their sample variance. And we computed the degrees of freedom from that big complicated formula as being just over 200. And now we're going to do a hypothesis test to see, are the means of these two samples, that is the age differences for the male skeletons compared to the age differences for the female skeletons. Are these two means equal or are they unequal? Well, the difference in the sample means, as we already saw, is equal to 4.2 years. But then the question is, does that tell us that mu1 minus mu2 is not equal to 0 either? Well, now we know how to compute a p-value. We'll say the p-value should be the probability that we would observe a difference in the sample means, which is at least as big as 4.2 years under the null hypothesis. So we do our old trick of subtracting off the mean, although in this case, mu1 minus mu2 is actually 0, but we can think of subtracting it off and then dividing by the square root of the sample variance again. And we do that to both sides. And then we say, well, the left-hand side is approximately the absolute value of a t-distribution with that number of degrees of freedom just over 200. And the right-hand side is just some number, and we can work it out. And we're saying, what's the probability that a t-distribution with that many degrees of freedom is bigger than or equal to 2.61? And the answer is that's pretty small. That's a little less than 1%. And so unless you have a very small significance level, you're probably going to say, well, we should reject H0. That means we would conclude that indeed mu1 is different from mu2. Indeed, the mean age difference for the male skeletons, even the true mean, is simply not the same as the true mean for the female skeletons. Okay, now let's do another example. Let's go back to that life expectancies example. And remember there we had one sample was the life expectancies in East Asia and the Pacific, and there were 30 countries there. The other sample was for South Asia, and there were 8 countries there. And they each had their own sample mean and their own sample variance. And again, we want to test the hypothesis that the two true means are equal versus the alternative that the two true means are not equal. Well, the observed difference in the sample means is here equal to 6.1 years. So the p-value should be the probability under H0 that the difference in the sample means would be at least as big as this 6.1 years. Well, again, we subtract off the mean even though it's 0. We divide by the square root of the sample variance that we compute, and we say it's the probability that the absolute value of a t-distribution with now the number of degrees of freedom is 9.09 is bigger than or equal to this number that when you plug it all in says is it bigger than or equal to 1.90. And that's approximately a 9% probability. Now that's not so small. So again, it would depend on your significance level, but probably you would say, no, we can't actually reject H0, and we would allow for the possibility that maybe these two means are equal. So maybe it's true that sort of a typical country from East Asia and the Pacific has the same average life expectancy as a typical country from South Asia. So now we know how to compare two means and how to get confidence intervals and do hypothesis tests, all using that same t-statistic that we developed at the beginning. As our final topic for this lecture, let's go back to that issue of pooling the estimates for the variance. So let's imagine now we're still doing a hypothesis test, but now it's a pool test, meaning that we're going to assume that the variances are equal for the two samples. We still want to test the same null hypothesis that the two sample means are equal versus the alternative that they're not equal. We still have this statistic from before which said that this quantity involving the differences of the sample means minus the differences of the true means was approximately a t-distribution. But now we're going to assume that the true variance is the same for the first sample as it is for the second sample. And that means that under H0, if we're trying to compute for the null hypothesis, we have the same mean and the variance, and then it turns out that we can pool the samples. So we come up with a common estimate of the variance for both samples together because we're assuming it's the same. And the formula for it is this pooled variance, which is kind of a weighted average of the individual sample variances of the two samples. Indeed, if the sample sizes are the same, then it's just half of one plus half of the other. If they're different, then we count the one that's a bigger sample a little bit more. But anyway, we get this pooled sample based on estimating the variance for the two samples put together. And the degrees of freedom in the t-distribution actually simplifies now. Under this assumption of equal variances, and where we're pooling the estimate for the variance, the number of degrees of freedom is simply the sum of the number of degrees of freedom for the two individual samples, namely n1 minus 1 for the first sample plus n2 minus 1 for the second sample. And that gives us a simple formula for the degrees of freedom, much simpler than that horrible complicated formula from before. So let's try this out in an example. Let's go back one more time to the skeletons. And again, we had the male skeletons, the 281 of them with their sample mean and variance. We had the female skeletons, 119 of them with their sample mean and variance. And we're still testing whether the means are equal versus whether they're unequal. But now we're going to assume that the true variances are the same for both genders. And if we assume that, then we can pool the variance estimator. And using that same formula, we get an S squared, this pooled variance, which works out to about 196.3. Now, we knew that the observed difference in the means was 4.2 years, and now the number of degrees of freedom is just n1 minus 1 plus n2 minus 1, which is equal to 398. So now we know how to compute a p-value, and indeed the p-value should be the probability, once again, that the observed sample difference would be at least as big as the 4.2 that we got. And, well, again, we can subtract and divide and say it should be the same as this other quantity being bigger than or equal to 4.2 divided by the square root of that sample variance. But one difference now is instead of using S1 squared and then S2 squared, we're using this pooled value S squared everywhere. Well, then we can continue the calculation, and it's the same as the probability that a t-distribution with our new number of degrees of freedom, namely 398, is bigger than or equal to this number that works out to 2.74, and the probability of that works out to 0.0064. So this is a p-value which is even a little bit smaller than the p-value we got when we didn't make that assumption. We didn't get the pooled estimate for the variance. And once again, we would probably say that we're going to reject the null hypothesis. And once again, we would say that the male skeletons do indeed have a different true mean age difference compared to the female skeletons. Okay, so whether we're doing a pooled version or an unpooled version, now we understand how to compare two different means from two independent samples and to use these two different forms of the t-distributions, and we can compute the confidence intervals, we can compute hypothesis tests without pooling and without assuming the variances are equal, and we can compute hypothesis tests with pooling when we do assume that the variances are equal. In this way, we understand a lot about how to compare two different independent sample means.